I've put together several examples of just different functional groups, different scenarios that can come up, and then also some example problems that you could see on like exam type question. I put this one in here because one, it shows again that ethyl splitting pattern, the quartet triplet, but also because it shows an OH group. Now, hydroxyls, OHs do not participate in splitting most of the time. So I'm going to put do not normally participate in splitting. And then the other thing about them is that the chemical shift can vary. Because it's sensitive to hydrogen bonding, to concentration, to pH. And the other thing about the OH is that oftentimes the signal is broadened out. Now in this case it happens to look pretty sharp, but we're going to see examples where the OH can look very broadened out and it won't integrate to a full 1. So we would expect this to have an integration value of 1, but a lot of times you're going to see that it's a little less than that. Here's an example of an aldehyde, just so you can see how far downfield this peak here shows up. That's one of the most deshielded types of protons that we'll see. The carboxylic acid, like the alcohol, is going to show up really broadened, may not integrate to a full 1, and it's much more deshielded than an alcohol OH. So look for that between 10 and 12. Let's talk about this one in terms of prediction. We have an A, B, C, D, E, F spin system here. If we were to assign splittings, we would have a singlet, a doublet, and then we have that quartet triplet splitting pattern. And we know that the aromatics are going to show up between 7 and 8 ppm. The NH group is going to be easy to tell because it, like an OH group, will look broadened. And so we're going to look for kind of a signal by itself that looks a little wider than the other ones. And then we have a singlet methyl group that should be pretty easy to tell. So let's take a look at the next slide. And here is the spectrum. So as I mentioned, here's that broadened out NH. Here are the two doublets that belong to the aromatics. Here's the quartet triplet splitting pattern of the ethyl group. And then finally the singlet that corresponds to this CH3 here. Once again, as far as which doublet peak is the one closer to oxygen versus nitrogen, if I had to guess, I would say that the oxygen is more deshielding, but to be 100% certain, you'd actually have to have more experimental data. Here's another situation that you can encounter. So you have an A-B system here with the two on the ends actually being identical. So protons A in the middle are going to be split into 1, 2, 3, 4 plus 1 equals 5. So it's going to be split into a quintet, and that's what we see here. So this is coming from the protons labeled A. B, on the other hand, is going to be split only by the two in the middle, and so that's going to be split into a 2 plus 1 or a triplet. So that's this one here. So we're going to call this B. And as far as integration goes, the values aren't on here, but you know that this should be a 4 to 2. It could be a 2 to 1, either one ratio there. And it makes sense that the protons that are labeled B are more deshielded because they're closer to the bromine. Here's another one. Let's do the same type of exercise. So I'm going to say we have an A, B, C, these are all the same. D, E system. In terms of splitting, we're going to have singlet, singlet, doublet. This is going to be a triplet down here at E. And D is going to be the most complex, so it's getting split into a doublet that's getting again split into a doublet. So this is, you could call this a multiplet if you want. And we know that the aromatic should be between 7 and 8 ppm. And then I would expect that B is going to be more deshielded than A, because not only is it next to a carbonyl, but it's in between the two aromatic rings, which are deshielding. And if you look here, we do have a singlet that's by itself. I'm going to say that that's this proton here. Then we have a taller singlet. That should be these protons up here. The rest of the stuff, all of this aromatic, is piling up on top of each other, which makes sense because these are mono-substituted benzenes. And so you're not going to be able to say much more than you know that these are C, D, and E. They're in there somewhere. You just can't say which one is which. And let's do one more. We have A, B, C, D, and E. We're going to have singlet, singlet, doublet, multiplet, triplet. And we know that these should be between 7 and 8. It should be fairly easy to tell because of the integration values. We have 3 to 2 here, which one's A and which one's B. So once again, you see those aromatics piled up on top of each other, so you're not going to be able to say for sure which one is which. If you take a look here, we have a more shielded signal that looks a little taller, and that makes sense that it's a CH3 because it's further away from this oxygen than this one is. That belongs to this set of protons here. So this is the CH2 group that's closer to the oxygen. And here's another type of question, just to label, to give letters to the protons. So A, B, C, D, and then say which one is which on the spectrum. So this is an ethyl group. It's going to have a quartet triplet splitting pattern. So I'm going to expect that the quartet coming from B, being closer to the oxygen, is going to be the most deshielded. So I'm going to say that that quartet here is B. The triplet is over here. That's A. Then we have 2 singlets, but one is representing 2 protons and one is representing 3 protons. So the integration values, even though they're not given, you can tell that the larger peak is the one representing the higher number of protons. So I'm going to say that that's D, and this is C. And I also feel comfortable saying that not just because of eyeballing the peak height, but because C is wedged in between 2 electron withdrawing groups, so it makes sense that it's more deshielded than D.